Well, we continue developing methods for studying Legendre's symbol. Now, Euler's method was our first step in computing the values of Legendre symbols. We hold it dear in our hearts because it was our first, but it's rarely practical for by-hand computation as it involves computing large exponents. Gauss's method was way more convenient. Basically, instead of doing the successive multiplication in order to compute the exponents in Euler's method, in order to generate the multiples in Gauss's method, you simply have to do repeated addition. But even this improvement eventually becomes impractical. To determine the value, for example, of the Legendre symbol 105 over 2111, which is a prime number, what we would have to do is compute 1055 successive multiples of 105. We might be able to do it, true, but it's going to be extremely tedious. But on the horizon, there's a very powerful technique that we're working towards, called the Law of Quadratic Reciprocity. That's a result that appears across numerous fields of math, and correspondingly there are many different ways to prove it. For example, there are some wonderfully elegant proofs involving abstract algebra. Now, the proof of this will appear in the next video. But since we don't assume familiarity with abstract algebra, what we're going to be doing is proving that very powerful theorem, the law of quadratic reciprocity, using only elementary techniques about how to count various objects. The elementary proofs usually rely on a variation of something known as Eisenstein's lemma as an intermediate step. This lemma on its own takes some time to prove, and that's what this video is about. So what is Eisenstein's lemma? Let P be an odd prime. Let A be relatively prime to P, and A also must be odd. Then define f of A to be the following sum. I goes from 1 to P minus 1 over 2, a value that we've seen pop up a lot in determining what is or isn't a quadratic residue. And the thing I'm adding up is this quotient IA over P. Now, something over P in square brackets is that quotient given by the division algorithm. So this is a whole number, and it's which multiple of P do I use in the division algorithm. And you can compute it as long as you're willing to work with non-integer values as simply what is the non-integer value K over P and round that down to the nearest integer. That's going to be how you can compute these quotients. Then, once we've done all of this, the Legendre symbol A over P is -1 to the f of A, where f of A is this sum as I goes from 1 to P minus 1 over 2 of these various quotients. So A is a quadratic residue modulo P if and only if this sum is even. We're not going to really use Eisenstein's lemma to compute Legendre symbols. Rather, it's an intermediate step in our forthcoming proof of the law of quadratic reciprocity. But let's at least see what the terms in the lemma represent. So we'll go through one specific example, the Legendre symbol 7 over 31, and we've actually already computed this. Now P is 31, that's an odd prime. A is 7, an odd number that's relatively prime to the base. So the lemma should apply. Note, by the way, Eisenstein's lemma requires that other number A to not just be relatively prime to P, but also be odd. This is a new requirement that was not present in either Euler or Gauss's methods. So then what we have to do is compute f of 7. That's going to be the sum as I goes from 1 to P minus 1 over 2 of the quotient 7 times I over 31. So I will have to go from 1 to 15. So we compute by rounding down. Okay, so we take I starting at 1. So 7 times 1, 7 times 2, times 3, times 4, times 5, times 6, times 7, times 8. We're going to have to go all the way up to 7 times 15. 7 over 31 rounds down to 0. So does 14 and 21 and 28 over 31. But 35 over 31 rounds down to 1, as do 42 over 31, 49 over 31, and 56 over 31. 63 over 31 rounds down to 2, 70 over 31 rounds down to 2, rounds down to 2, to 2, to 2, but 98 and 105 over 31 both round down to 3. And 105 over 31 is 7 times 15 over 31, so that's my last term in this sum. So the individual terms in this sum are 0, 0, 0, 0, 1, 1, 1, 1, 2, 2, 2, 2, 2, 3, and 3. So we add all of those up and we get an even quantity. So according to Eisenstein's lemma, The Legendre symbol 7 by 31 is -1 to the 20th power, which is +1. In other words, 7 is a quadratic residue modulo 31, and that does match with how we have already computed that Legendre symbol. So we worked through an example to get familiar with the terms in Eisenstein's lemma. Let's actually approach the proof. Remember, P is prime and odd. A is relatively prime to P, as has always been the case, but now we're also assuming that A is odd, unlike our earlier techniques. Some of the steps are going to be fairly similar to Gauss's method. We're going to list out I from 1 to P minus 1 over 2, and we're going to compute these quotients IA over P. Each multiple IA from the division algorithm can be written as that quotient times P plus a remainder. Just as in Gauss's method, we're going to list out all of those remainders and call it S prime, which we rewrite as the small remainders followed by the large ones in increasing order. So all of the BI's are less than or equal to P minus 1 over 2, and all of the CI's are larger than P minus 1 over 2. So this is identical so far to Gauss's method. Now, 1 through P minus 1 is the standard reduced residue system mod P, and A is relatively prime to it. So if I listed out all of the multiples of A all the way to P minus 1 times A, this would be a reduced residue system mod P, and therefore all of these would be distinct values mod P. S prime is the list of some remainders which correspond mod P to multiples of A. It's therefore equivalent modulo P to a subset of this, and since all of these are distinct mod P, S prime are all distinct mod P. This is also a step in the argument of Gauss's method. So if we were to sum up the equation given by the division algorithm, so for each I going from 1 to P minus 1 over 2, I'm going to sum up the left, but I'm also going to sum up this thing on the right. Then the remainders can be split up into the big terms and the small terms. So on the left, we just sum IA as I goes from 1 to P minus 1 over 2. This term here, we're also summing up as I goes from 1 to P minus 1 over 2. Then the remainders get summed up as I goes from 1 to P minus 1 over 2. But these remainders just go through this set here. This is the set of remainders. So instead of adding them up in the order they were generated, what I'm instead going to do is add up all the small remainders and then add up all the big remainders. The BI, remember, are the small ones. The CI are the big ones. Now notice how many small remainders are there. The first one is B1 and it ends at index M, so this sum goes from 1 to M. How many big remainders are there? They go from index 1 to N, so this sum goes from 1 to N. So altogether, these two terms here simply add up all the remainders we generated, so it corresponds to this single sum here. So by adding up the left, we got this. By adding up the right, we transformed it to look like that. So these two things must be equal just by adding up the division algorithm over and over again. All right, so now what we're going to do is we're going to play around with these various sums we've generated. So far we've written this. Remember, the BI's are the small remainders and the CI's are the big ones. From the first sum, we can factor out the constant A. And from the second sum, in other words, the first one on the right-hand side, we can factor out the constant P. Okay, in which case we get this. This is A times this sum of i's is equal to P times this sum plus these two things that we haven't touched yet. Now this P has been factored out, but this sum of all of these quotients is exactly what we defined as f of A. So A times this sum is equal to P times f of A plus the sum of the small remainders plus the sum of the big ones. One step in the proof of Gauss's method was to show that if the big remainders were replaced with P minus them, as a set, you simply got all of these values from 1 to P minus 1 over 2. Therefore, if I was just to sum up all of these, okay, this line here, by the way, is not related to this one. It's just related to this line. So if I sum up all of these values, that will be the same as summing up all of the B's, followed by summing up all of the P minus C's. Now I can distribute this sum. I sum up from 1 to n the constant P. That just gives me n times P. And then I have minus the sum of all the C's. So the sum of all of the i's, just as I goes from 1 to P minus 1 over 2, is actually the sum of the small remainders plus this multiple of p minus the sum of the big remainders. So we have two equations that we have generated. First, we were able to show that a times the sum as I goes from 1 to p minus 1 over 2 is p times our f of a, this was the sum of all of the various quotients, plus all of the remainders, the small ones and the big ones. On the other hand, the sum of all the i's, we were able to express as the small remainders plus a multiple of p minus the big remainders. So I now have two different equations. I'm going to subtract the second from the first, and that gives me, well, I have a common factor of this sum. So I have a of them minus one of them. So on the left-hand side, I have a minus 1 times that sum. And here I get p f of a. This sum of the small remainders, when I take away the sum of the small remainders, will cancel out. I do have to subtract this multiple of p. Now the sum of the big remainders minus negative the sum of the big remainders just gives me 2 of them. So a minus 1 times this sum is p times f of a, where f of a was the sum of all the quotients, minus a multiple of p plus 2 times the sum of the big remainders. Now let's look at this modulo 2. P was an odd prime, so modulo 2, it's equivalent to 1. A was assumed to be odd, which means a minus 1 is even and therefore equivalent to 0 mod 2, and certainly 2 is equivalent to 0 mod 2. Here is where the assumption that a is odd comes in. A being odd allows me to assume that a minus 1 is equivalent to 0 mod 2. So if I take this equality and I say, let's replace values with what they're equivalent to modulo 2, this is 0, so that sum disappears. P was equivalent to 1 because P was odd. P is equivalent to 1 because P is odd, and this is just a 0 anyway because it's 2. So f of a is equivalent to n modulo 2. All right, so where are we? P is an odd prime. A is an odd number relatively prime to P. F of a was this sum of quotients. And we have shown that f of a is equivalent to n modulo 2, where n is how many of the remainders are big. Gauss's method tells us the Legendre symbol can be computed as -1 to the n. That really only depends on whether n is even or odd. In other words, is it equivalent to 0 mod 2 or to 1 mod 2? I don't actually care if n is 40, 50, 60, etc. If it's any even number, -1 to that power spits out a 1. Similarly, -1 to any odd power will spit out a -1 regardless of what that power was, so long as it was odd. So we've shown f of a is equivalent to n mod 2. So either they're both even, they're both equivalent to 0, or they're both odd, they're both equivalent to 1 modulo 2. So f of a isn't necessarily equal to n, but -1 to the n will be equal to -1 to the f of a, because either both exponents are even or both are odd. Even if they're different numbers, they're either both even or both odd. Therefore, these are the same number, and since we already know the Legendre symbol is equal to -1 to the n, it must also be equal to -1 to the f of a. And that's the statement of Eisenstein's lemma, that instead of computing the Legendre symbol as -1 to the n, where n is counting how many remainders are big, you can instead compute the Legendre symbol as -1 to the f of a, where f of a is this sum of all of these quotients from the division algorithm. So let's talk about Eisenstein's lemma a little bit. We already mentioned we're not really going to use it to compute values of Legendre symbols. Gauss's method is not really any more work. Both involve repeatedly applying the division algorithm. In Eisenstein's lemma, you keep track of the sum of the quotients, whereas in Gauss's method, you keep track of how many remainders are big. But you really have to keep working through all of these multiples and keep applying the division algorithm. However, Eisenstein's lemma requires a to be odd, and Gauss's method does not. So they're really an equivalent amount of work, and Gauss's method will work whether a is even or odd. Eisenstein's lemma specifically required a to be odd. So we're not really going to be using it to compute the value of Legendre symbols. What it is it's one step in the proof of the law of quadratic reciprocity. And given that we've spent about 15 minutes proving Eisenstein's lemma, it was worth doing as a separate video rather than it being part of the proof of the law of quadratic reciprocity. So Eisenstein's lemma, not something we're going to use computationally, but it is going to be a very important step in the next video.